Ladies and gentlemen, and respected scientists, I'm China Dr. Zhang. This time I'm in Belarus as the visiting scholar from the National Academy of Sciences, Belarus. Today, my presentation is on the topic of supercomputing modeling the monocrystalline silicon growth. Dr. Medvedev from the National Academy of Sciences of Belarus is leading research of this project. Monocrystalline silicon is widely used in the semiconductor industry. Over 19% of integrated circuit devices are fabricated on it. The purity of crystal structure is very important for the stability of electrical properties. Currently, the most productive method for monocrystalline silicon growing is the Czechoslovakian method. When it were implemented into practice, it brings a significant process in the development of the artificial growth of crystals. The CZ process involves the transformation of polycrystalline silicon into monocrystalline silicon through a crystal pulling equipment. To be used in microelectronics, the crystal of monocrystalline silicon should be followed by a series of treatments, as you see this slide. The whole procedure is very complicated. It means that each stage of the procedure is crucial to the quality and yield of the final product. I will make a brief introduce about the CZ method for growing crystal. The crystal equipment involves heating high purity semiconductor-grade polycrystalline silicon to a molten state within a container, like this, inside container. A crystal seed is placed on the end of the predetermined orientation polycrystalline rod, which is then immersed into the molten silicon. Subsequently, the polycrystalline silicon rod is slowly pulled upward while simultaneously rotating. In practice, the engineer watches the process from the window to make judge when should he start to lift the seed, and the crystal growing is ready. It could take 2 hours and more. That crystal is formed to be lifted. These pictures are from 3 experiments. The fluctuation of the diameter will affect the quality of the crystal. The uniform diameter of crystal is the most important criterion for monocrystal silicon. Growing with a monocrystal with a diameter of 300 millimeters and a length about 2 meters takes about more than 50 hours, with material costs alone exceeding $4,000. And if there is a need to change a thermal field, the costs increase to over $14,000. The precise observation of physical processes is difficult for high temperature, vacuum, and airtightness. It does not include the combined influence of large-scale physical characteristics and small-scale particles or microstructures. It is necessary to consider not only overall physical conditions, but also interactions of particles at the macroscopic level. It was the reason why we start our research on three-dimension models on supercomputer to elastina technology. Supercomputer can deal with complex dynamic models for calculating. In our primary research, we create kinetic and thermodynamic monocrystal models on supercomputer. The purpose of research to gain a deep understanding of crystal growth process, simulating and analyzing various influence factors, optimizing growth conditions, and improving crystal quality and growth efficiency. You see the characteristics of supercomputer, which let us establish a three-dimensional model analyzing the dynamic characteristics of the melt near the solidification. Three-dimension geometric and finite element models of the main process of crystal growth, such as seed, molten silicon, and container. In the established dynamic CZ model, the seed and the container rotate in opposite directions, while the seed simultaneously grows upward. From the modeling, we can see the velocity from Z-plane of melt. Also can see the velocity of the seed. It means we can quantitatively analysis of crystalline volume and growth time in adding conditions what we expected. And also, temperature distribution is calculated to help us to check the result, correct or not. From thermal calculating, we can get the crystalline volume and growing time under identical conditions. This calculation was performed over 14,400 seconds in elastina, yielding the resultant velocity distribution for a duration of 4 hours, including both minimum and maximum values. The information is highly valuable for understanding the dynamic behavior of the system and the potential events that may occur during the simulation process. Our research in preliminary stage, supercomputer modeling can help us to observe the growth behavior of crystal, such as the solidification phenomenon beneath the seed. It can assist engineers in making informed decisions, replacing reliance solely on experience and thereby improving production efficiency. In our detailed plan stage, we will build a comprehensive model of crystal growth process on a supercomputing, calculating the entire life cycle of crystal growth. We will analyze the physical behaviors causing diameter fluctuations and propose effective improvement measurements. Establishing a digital twin system for CZ monocrystalline silicon growth using a supercomputer to address practical engineering application issues. We know different methods for crystal growth, each with its own characteristics. We may attempt to leverage the advantages of certain crystal growth technology to assist in study of monocrystal growth using CZ method. The supercomputer modeling monocrystal structures, it could be used in different crystal growth methods. Thank you very much for your attention.